Alrighty, let's begin with a little bit of process here. So this is a school. It's not a conference. All right? So that means that you're supposed to be asking questions. You're supposed to be thinking. Now that means that we need to figure out a way to make sure you do that. So Kathy and Neil and I have been talking, although they don't know it, about how we're going to do this. So our feeling is that there should be roughly 100 questions at least during this school. That comes out to about 20 a day, roughly 4 per lecture. Now either you ask those questions, or we will ask you 100 minus however many you've asked on Friday. You notice those open sessions on Friday? That's for examination. If you ask 100 questions, there will be no examination. We will all go skiing. If you ask as many questions as you've asked so far, there will be no skiing on Friday. Yes, Richard?
Can I ask 100 questions in this talk?
No. Second, our goal is not to get through all of the material. Our goal is for you to learn. All right? So pace is not key here. We don't need to rush. And so don't hesitate to ask questions because we have so much to present. If we don't get through it, you can read it later. All right? The goal is to have interaction. And in that same spirit, the last thing I might mention is that the 3 of us are native English speakers. Different English, but nonetheless native English speakers. And as a consequence, occasionally we may talk too fast, especially for those of you who have traveled thousands of miles. I once gave a talk at an IAU, in a General Assembly. A friend of mine came up, a good friend as you can tell, and he said, "Bob, that was one of the best talks I've ever heard. I only wish the audience understood it," because I was talking too fast. Now, I will try to stay slow, but please don't hesitate. I have so much admiration for all of you who are multilingual, because I am not. And the least I can do is try to be as clear as I can. Now, Neil said that he sort of broke up our roles in scale size. I'd break up our roles a little differently. The way I see it is that today Neil and I are trying to tell you the products of star formation and star-forming regions. And then roughly for the rest of the week, Kathy is going to explain it. All right? So that's kind of the logic here. We're going to tell you what is, and she's going to tell you why. All right? So on that note, let's start with open clusters. Neil was telling you about the field distribution. I always have a tendency to start with beautiful pictures because this is how I began. This is the open cluster M35, which I'll be talking about a fair bit this evening. This is actually another open cluster, NGC 2158. For those of us who work on M35, this cluster is a bit annoying because it actually extends, the tidal radius is easily out to here. But nonetheless, it is a gorgeous pairing. I remember when I was working on M35 and he said, "Are you sure you don't have NGC 2158 members in here?" And I said, "NGC 2158?" because my photographic plate was this big. And I was just stunned that he knew it was there. And that's what old people like me know. So that is NGC 2158, and it is a beautiful slide. And I think maybe the key word on here is that for today, we're talking about classical open clusters because we are talking about the product of the regions. The next few days, we'll talk about embedded clusters and so on. Roughly, this is what I'd like to cover: definition, global properties, internal properties of clusters, a bit on associations, and if time permits, but if it doesn't, it's okay, an indulgence at the end on what I'm working on right now. So in terms of definition, first, at least for the traditional, classical open clusters, the age needs to be much, much longer than the time scale for the loss of the gas. Neil mentioned that these embedded clusters, much of their dynamics is affected by the gas, and it's absolutely true. And we'll get to that. But for a classical cluster, its age needs to be long enough that the gas has disappeared, and that's a scale of a few mega years. So that's roughly the youngest that we'll be talking about. When I talk about stellar dynamics tomorrow, this may be a little more clear, But it's very important that the age of the cluster also be larger than the dynamical scale, or the crossing time, essentially to know that it's bound. And so that's a second criteria. Roughly speaking, these are not really criteria as much as observed facts that allow us to classify. I don't think the 10 to the fourth will surprise anyone. People might say 10 solar masses for an open cluster? Well, I put this here more to make a point, in that the range between an open cluster and what I would call a multiple system really has to do with whether we're talking about random dynamical encounters in a system or a hierarchical system essentially in Keplerian motion that is stable more or less for infinity. And so that break point between an open cluster dynamics and a multiple system dynamics really has to do with the type of orbits that the stars have. Truly, this is rather low. 100 is more reasonable.
Does the mass range include the stellar association?
I'm sorry, include?
So the mass range
Yes.
of open cluster, does it include the stellar association or OB association?
Not yet. We'll get to that. Yes, it does, but this would not. This would not be an association. That was one question, Richard. Could you keep track, please, back there? That was one question. Okay. That's your contribution. As Neil pointed out, the metallicity tends to be within a factor of few of solar. This is not, again, as much a defining property as an observed property, but nonetheless, as Neil said, allows us to distinguish this type of cluster from others. And in the same spirit, location in the Milky Way disk, which I'll talk about in just a second. There's been roughly 2,000 open clusters identified. The Lunt catalog used to be sort of the go-to catalog. Now Diaz and his colleagues have taken over, if you want to really sort of see what's known. This, as Ivan once said to me, be wary of any compilation. Those who use compilations for their science deserve what they get, was the way he phrased it. And what that means is you have a very heterogeneous catalog in terms of both the knowledge and the quality, but nonetheless, it's a good place to start. And within roughly 850 parsecs, and I'll show this in just a second where that comes from, within roughly a kiloparsec, there's about 250 open clusters by these definitions. All right. So first I'm going to talk about the global properties, the broad scale properties of open clusters, which you should know I don't work on. So this is another important thing about the school. This presumption that we are experts and you are not is absolutely wrong. You know, as a union, you have far more knowledge than I have. And so if I say something wrong, or more importantly, if you can add, please do. So I asked Bob Benjamin to place the Diaz catalog on the GLIMPS, being from Wisconsin, the Spitzer GLIMPS survey of the galaxy. It's amazing to me as someone from Wisconsin how quickly the bar has become sort of standard operating procedure, considering how excited we were 5 years ago to discover it. I wasn't part of that. But this is the glimpse model of the galaxy. This is the Diaz catalog. This is 8 kiloparsecs, 4 kiloparsecs. Obviously very, very biased towards the solar region. The blue here are a very interesting sample of massive clusters that perhaps we'll have some time to talk about. Bob and I blew it up a little bit to see if we could actually see an association of the Diaz catalog with the arms. And I would argue that the answer is no. And I suspect that reflects more on the quality of the distances. And as Neil was saying, the ages, but in this case, the distances within the catalog. Again, a heterogeneous compilation. Gaia, of course, will make that picture irrelevant. But this is important for the discussion here. This is a very nice piece of work by a collaboration including Piskunov and Rezer and Zinneker. This is actually it's not using the Diaz catalog, except that it used the catalog to go to the ACSS and survey for open clusters, the all-sky catalog of stars. And this is a plot of surface density versus distance from the sun in kiloparsecs. And you can see where that 850 parsec limit that I mentioned in the earlier slide came from. Roughly, they see their completeness as dropping off here. This is the Gould belt that I'm sure we'll talk about at some length. So roughly speaking, this is the average density, about 100 per kiloparsec squared. The Gould belt is an excess over that. So within a kiloparsec, looks like we may be complete. Now this is a nice picture from another annual review by Simon. And this is, you've already seen. I mainly wanted to show this. Neil made reference to this. The blue are the young open clusters. The red are the older open clusters, greater than 3 gig a year. And you'll notice that they tend to be out of the disk. And odds are that's a dynamical effect in the sense that clusters which are in the disk are continually buffeted by molecular clouds and other dynamical interactions and tend to evaporate and disappear. And so the older clusters that are out of the disk have calmer lives, shall we say. Now, just to be clear, the slides like this are very dangerous because students, I'm sure none of you, but students look at these and see that up there and say it's way out of the disk. But remember, it's doing this constantly. So it is interacting with the disk, but on a less frequent basis. But you do have to remember that they are constantly in motion in the z direction. So roughly speaking, we've got a scale height of about 50 parsecs compared to the 300 that Neil was mentioning. Surface density of about 100 per kiloparsec squared. Volume density of about 1,000 per kiloparsec cubed, but of course you don't have 1,000 kiloparsecs in height, or even a kiloparsec in height, excuse me. And so this is a little bit misleading. This is a little more meaningful, but about 100,000 in the Milky Way or so. Please.
So it may be worth adding that that's the same scale height as of gas disk.
Exactly. That's exactly right. Thank you. That's 2. Okay. The luminosity function, I have to confess, I've never found luminosity functions very illuminating. I apologize for the pun. But it's more interesting when you turn them into masses. But I did want to at least point out that the luminosity function of the open clusters in the galaxy has a slope which is very similar to what we're seeing for extragalactic clusters. And of course, in the galaxy, we can go to much smaller clusters. The claim is that this turnover is real, probably due to dynamics. We'll come back to that. I've lived long enough to know that most turnovers, many turnovers, go away. But we shall see, and Gaia will help us with that as well. Now, masses. How do we get masses? It's not easy. Oh, everything will be easy after Gaia, but at the moment it's not easy. One way is simply to do a complete census. You just count every star. That's straightforward. Of course, you have to assign a mass, and you have to know which ones are members, and we'll come back to all of that. But roughly speaking, you can do a complete census, but you know that at some point you're not going to get down to the smallest stars, and you know you're not going to get to the largest radii, or a good chance you won't get to the largest radii. So you have to make corrections for that. And especially for this, it depends, as Neil said, on your initial mass function. And there's a lot of sensitivity in your mass to what initial mass function you choose for the lower end. A comment on radius, by the way. This is a pet peeve of my own. But radii for clusters are largely meaningless. They typically are the result of examination of an image on a plate by somebody. And when you use those data to try to do anything astrophysical, you don't know what you're working with. If you're going to work with clusters, make sure you're either working with a core radius, a half mass radius, a tidal radius if you have it, okay? But don't take radii out of papers unless they tell you what they're using. Because typically, it depends on the background field. It's usually a measure of where the cluster appears to disappear. And it's just meaningless, absolutely meaningless. Another way to get the mass is dynamical, using a virial process. As I'll show you, this is really hard, mainly because the dispersions are so small. And I'll be interested to talk to you a little bit about whether the binaries are going to affect Gaia in terms of doing that. And then finally, Ivan had this approach, which is a dynamical model fitting approach. If you know your tidal radius, then you know your mass. It's a beautiful, elegant idea. It just unfortunately depends on the tidal radius cubed. And that's a problem for getting masses. So the point is, it's hard to get masses of clusters, even globular clusters, even the exotic clusters in other galaxies. If you want to do it accurately, and I mean accurately as compared to precisely, it's hard. That said, this particular group used tidal masses. This gives you a sense of the mass distribution of current open clusters, not initial, current, from about, in this case, 10 solar masses up to maybe 10,000. So that's the range we're talking about, with an average mass of about 700 solar masses. That's a number you want to keep in your mind because Kathy's going to explain why that is, okay? It's about 700 or so is a typical bound cluster. And I emphasize that. It's a typical bound cluster. Okay. Okay. This is a nice figure that Simon and his collaborators put together. This is half mass radius versus mass for open clusters, the subject of their review, which are massive, new massive young clusters, newly discovered, and globular clusters. And there's a couple things here that are important to sort of change common misperceptions. The first thing you'll notice is that the half mass radii aren't that different. Okay? This is the half mass radii of open clusters and globular clusters. They're roughly the same in size. Yes, the densities here are higher because they have more stars, but their sizes are actually very, very comparable. Now the masses are quite different. Again, 10 to 10,000 versus 10 to the 5th and 10 to the 6th. Even density is not as different as you might think, right? Between here and here is 2 orders of magnitude. So this range in which the open clusters sit is actually includes quite a few globular clusters as well. Right? Now notice these are half mass radii. The central densities, especially of collapsed globular clusters, can be very, very high.
Can you say again what is on the x-axis and on the y-axis?
This is mass, logarithm of mass, so that's 10 to the 4th. And this is half mass radius. Well defined, half mass radius. But again, my point is that this concept of globular clusters as being just tremendously denser than open clusters is a little bit of a misnomer, at least in the global sense of half mass radii. Core densities can be very high. The other curves are relaxation times, but we'll come back to that. And I just did want to point out, and perhaps Michael will help with this because I know he's been working on this a bit, but I think later, not right now, we do need to talk about the role of these new young massive clusters in the whole picture. It's really a new phenomenon.
What are the typical error bars on this?
On these data?
Yeah.
Honestly, I have to tell you, I don't know. These are logarithmic scales, so I suspect they're very small on the logarithm scale. I would say a typical open cluster mass error would be a factor of a few. So depending on where you are in the log, perhaps like that.
So what about the uncertainties in the half mass radii?
That depends on the quality of the scientist. And I'm not sure. Mine are typically about a tenth of a parsec or so.
Even though you can have...
I'm kidding.
Okay.
Now, if you take those masses and you look at mass functions, again, we're looking at global properties here, you see this phenomena of a power law fit, really, a power law distribution that then tends to flatten off as you get to lower masses. This is sort of a common phenomena among bound open clusters, and I want to keep emphasizing that. These are the bound open clusters. Again, this power law is similar to what is seen in other galaxies. The other thing that's particularly interesting here is that I think what they've done is divided by age here, essentially. These are less than 10 to the 7th years or so, and you'll notice that there starts to be a tilt coming across here. And this slope, which I know in the back is hard to read, but this is a slope of minus 1.7 here. The tilting is not a big surprise. As clusters get older, they tend to evaporate. And if you have a largest cluster, then what's really happening is that the large clusters are moving into the smaller clusters, leading to a tilt in the slope. What's more interesting, I think, and more relevant to this school, is this result that I'll be talking about again in a couple days. But this is the distribution for the embedded clusters. This is what's actually known. And as Neil said, we fit a straight line to a few data. And if you do that and extrapolate out, the slope here actually is about minus 1.7 for the embedded clusters. About the same as that blue line.
So,
Please.
for GMCs, that's the same slope. Does that mean that you're essentially just mapping the GMC mass spectrum and thereby also including unbound negotiations?
Now I want to be a little careful here. You're saying that the GMC distribution is that slope, because I'm not showing the GMC distribution here. Okay. You tell me. Or you ask her.
It's about two as well, isn't it?
Yes.
So
Mhm.
it's sort of intermediate between those two kinds.
So what he's asking essentially is a question we've been asking ever since giant molecular clouds were discovered, is whether the clumpy structure within the GMCs is essentially the same structure, the same slope as we see in IMS clusters and so on. Well, I'm sure we'll talk about that more. The interesting thing is that the formation rate here for the clusters is about 0.4 per kiloparsec squared per megayear squared. The formation rate here is about 10 times that.
Right. In the right panel, what is again the dashed line? It's the completeness, the vertical dashed line.
This?
Yes.
That's their break point between the power law fit and the turnover.
Just observational.
So it's not a completeness, it's to guide the eye, essentially, on where the break is happening. Oh, yes, my heavens. Okay, good. Yes.
Why does dynamical evolution make a mass function steeper? Should it make it flatter? So if you have older clusters and you start by 1.7, it should have a slope of less than 1.7.
Well, what would happen if I were to essentially keep these clusters here and remove these?
Well, why would you just remove the low mass ones as well?
Well, now we'll get into the talk I'm going to give tomorrow evening, but essentially, if you have a cutoff here and you keep moving clusters that way, it depends on the cluster loss rate. And these are going to evaporate, I would argue, faster than these. But I agree that that's not entirely self-evident.
If there's a Schechter-like truncation, you can get the steepening of mass and lower masses full rate.
The point I was trying to make is that it's this difference of a factor of 10 that leads to the current statement that I'm sure we'll hear many times during this meeting, that roughly 10% of the stars are made in open clusters. I'll come back to whether I believe that or not, but the similarity of this slope and this slope has led to a general conception that because there are so many more of these than are seen over here, these must disappear with the loss of their gas. And what's left behind, and this is a sample of more massive clusters, is this end of the distribution, which turns into this. Okay. That's sort of the broad picture that we're going to be talking about quite a bit. I will say that as someone who's been around longer than most of you, I have seen this number switch back and forth like a pendulum over the years. From Roberts in the 50s saying that all stars were in clusters when I was just a boy, literally when I was just a boy, to no stars were made in clusters. And all I'm saying is I personally have some caution in the sense that remember that just because the things we say today are today doesn't make them true. All right. Please, first.
Yeah, For the embedded clusters, are these the masses of the entire star-forming region, or just the stellar component?
Oh, it's just, this is just the stellar component.
Okay.
Good question. Did you? Good. All right, you're catching up on your numbers here. Age distribution in this case, this is sort of the classic study by Whelan. This is a more modern approach of 100, this is again age versus essentially number, again logarithmic. And this is the volume limited sample. And you see this sharp drop off here, which is taken to be evidence for dynamical evolution. And we'll talk about that a bit tomorrow. There is some difference between 1971 and today, but the mean lifetime, and this is another number to remember, is about 300 megayears. Right? And what's the mean mass, by the way? Yowza! Well done, well done. All right, and a mean lifetime of about 300 megayear. All right, so keep those two numbers in mind. All right, very good. I actually put this up here, to be honest, just to tweak Neil a little bit and to be provocative. I have no idea about the truth of this. It's in a recent review, and I just thought I'd throw it out there. They go through the open cluster mass loss rate. They asked what is the total open cluster mass contribution to the thin disk, total stellar mass formed in the thin disk, put it together, and they find 33% coming out of open clusters. I'm not standing behind this in any way. I'm simply saying that I think we need and you need to be constantly careful and recognize history and recognize that numbers do change from the current number. And with that 10% that's going to be very important to the conversations this week should at least be considered with care, because this is science and you should try and go out and confirm it. So let me stop there. Those are the global properties. Any questions on those? Okay. Now the internal properties of the clusters. Happens to be my favorite cluster. It's probably the one of least interest to this meeting because it's 7 gigayears old. But it makes a point, which is, as Neil was saying, which of these stars are members of the cluster? And until you know, it's hard to do any science. If you take all of the stars in that field and you plot them on a color magnitude diagram, in this case B minus V versus V, it looks like this. There's no doubt the cluster is there, and there's no doubt that there's a bit of a giant branch there, although it may not be entirely obvious which ones are the giants in the cluster. I would argue there's some doubt as to whether there's any blue stragglers there, which happens to be my indulgence if I have time. And so how do we figure out which are which? Well, in a nutshell, and this is one place where I'll argue with Neil a little bit for fun so we can talk about it. Neil said it's not an and question as you go through the characteristics. I would actually argue if you go all through the characteristics and require that they all work, you're going to miss all the interesting stars. So I think the one thing that actually is clearly necessary for membership is kinematic association in 3 dimensions, and preferably distance association, if you can get that precision, in the cluster. So Imants Plateus measured proper motions down to roughly 22nd magnitude in this cluster. This is the proper motion distribution, and you can see the cluster right there, and you can see the field scattered throughout. So at some very simple conceptual level, that's the cluster. Those stars are the cluster members. Okay. Operationally, and this comes under techniques as Neil was doing as well, what you actually do is you fit a 2-dimensional Gaussian to this distribution. This happens to be 1-dimensional. This is one I did in radial velocity, but the concept is the same. For a good case, and this is far better than that actually, you get a beautiful peak where the cluster lies, excuse me, and then you get a very broad distribution of the field. I do want to emphasize, however, that no matter how broad your field is, this is the fit, that dashed line is the fit to the field, this is the fit to the cluster. There are some stars in there which are from the field. You cannot avoid it. Hopefully, as your precision gets better and better, I was going to say Gaia will shrink this down, but Gaia actually will not shrink this down because this is the actual velocities of the cluster itself. But as your precisions get better, then the amount of the field distribution that's within your cluster distribution gets as small as possible, and your contamination gets less, but you can never get it to zero. And you convert that into what's known as a membership probability diagram. This is a very clean separation. I'm showing you the best, okay? These are high 90% probability members, 0% probability members. Of course, there's always a distribution in between, but that's how you clean it out, and preferably in 3 dimensions. And when you do that, life is good, right? Here are the blue stragglers, here are the giants, clean, relatively clean main sequence, but I do want to emphasize, especially for all of you who use Gaia eventually, that these are probabilities, right? Bill Van Altena once made that argument to me very clearly. If you have a set of 99% probability stars, if you have 1,000 of them, don't forget that 1 or 2 of them will be field stars. And if you decide to write a paper on this fascinating star here, you better be darn sure that your probabilities of membership are meaningful. Now that said, and this is why I'm playing with Neil a little bit here, if you were to require CMD membership, which would mean on this isochrone, you would miss the blue stragglers here. And these are the colliding stars. These are the interface of stellar evolution and stellar dynamics. This is the hot subject in the field right now. So to my mind, it's kinematics, 3-dimensional kinematics plus distance, that really indicate membership. Okay. We can now do this with radial velocities as well. We do it at WIN. Flames is doing it at the VLT beautifully. And in this particular case, I'll just drive home a point that I may not have time to make later. All of these filled in circles are binary stars. So just make sure when you're studying a star that you don't think it's 1 star when it's 2. Now the spatial distributions, something that really has gone back a long way, but I want to make one primary point. This is M11, 200 mega years. And if you fit King models to this, and Neil, I had to laugh. Where are you, Neil? I had to laugh when you showed from your thesis. I didn't have the guts to reference Mathieu 1983 on here. Oh, that wasn't your thesis? Well, this is from Mathieu 1983, okay, and I didn't have the guts to say it because I figured all the kids in the room would say, oh my God, what an old fellow. But the cluster hasn't changed in 30 years. This is a fit of King models to different masses. 1 solar mass, 3.5 solar masses. I'll show you a more demonstrative example later, but even if you look at these, here's the core radius for the 3.5 solar mass stars. Here's the core radius for the 1 solar mass stars. You can see visually that the more massive stars are more centrally concentrated than the lower mass stars. And that shows up, this is really the better technique, which is a cumulative distribution. I think Neil was speaking about this a little bit as well. This is a very powerful technique for studying star-forming regions, for studying really any system. You can immediately apply the Kolmogorov-Smirnov test to this, but all I'm really showing you is that this is the distribution of the 3.5 solar mass stars, the 1 solar mass stars, and this phenomena, which we'll talk about, is called mass segregation. Okay, so when we talk about mass segregation, we're talking about the fact that the more massive stars are more centrally concentrated. Again, visually, we work in log space, and you really need to appreciate this figure. This is a log figure. Ever since Ivan first plotted it, it's been a log figure. So when you look at a picture like this, remember I was talking about radii? I don't know exactly where you would draw the radius for this cluster, but I'm guessing maybe something like this. The tidal radius for this cluster is out here, okay? Don't ever forget that, right? This is where all the power is in terms of both because of mass segregation and because of the isothermal concentration in the center. But these things are far larger than visually that you might think. Now, I mentioned virial dispersions, stellar velocity dispersions, both in these clusters and in the regions that we're going to study, are very small. They're under 1 kilometer per second. This is a recent paper we did on 188. It's about 0.5 kilometer per second. Now, I know in this day and age, you're all used to exoplanets, right? And exoplanets are, 50 meters per second. Beautiful data. They're on bright stars, okay? They're on stars of 10, 11, 12 magnitude. I don't even get started there. I'm like Gaia, right? I mean, the stars that I'm working on in this cluster are 13 to 17, roughly, in magnitude. So we don't have any trouble getting the precision that we need here, but I just want you to appreciate that we're still at a place, especially with 4-meter class telescopes, with 8 and 10 meter class, we're in a somewhat better place on precision, that we can measure velocities adequate to measure these dispersions, but it's hard work. I mean, you have to be careful about it. And maybe later today I'll talk a little bit about measuring radial velocities. But that's not the big problem. And this is really important if you decide to work on kinematics in star-forming regions. This is the problem. This is a lousy figure, but will make my point. So here's the point. You go out and use flames. You put 300 fibers down on a cluster, a young star-forming region. You get this beautiful dispersion. You compute mean v squared minus the mean squared. You get a dispersion. You publish. Guaranteed it is wrong. Absolutely guaranteed it is wrong, because within all of those velocities are the internal motions of roughly 50% of the stars that are binaries. So what you're measuring is both the internal motions of the system itself convolved with the orbital motions of the binaries. Now, if you make multiple observations, you'll be able to pull out the short period binaries. But the short period binaries aren't your problem, because the short period binaries have high velocities. They were way out in the tail in the first place. You probably didn't include them. The ones that are messing you up are the long period binaries that have orbital motions of a few kilometers per second. They're the ones that are sitting in the tail of your velocity distribution. And especially on the time scale of a dissertation, you're not going to know it, okay? That was my problem, all right? So I did some explorations, which 30 years later a student of mine redid, and thank God he found out they were right. But it wasn't that hard. Basically, I took a binary population, Apton, Levy, Duquesnoy, Mayor, Rodga-Heaven, whatever you want to use, and just play the game. Just do a Monte Carlo analysis at a certain binary frequency of what root mean square you compute at dispersions of 0.3, 0.5, and 0.7 kilometers per second. Let's do 0.3 just to exaggerate. Not to exaggerate, it's real, but I mean to really make the point. This is 0.3 kilometers per second. This solid line here is the root mean square that you'll compute. So you're out here. You're computing masses out here when the actual value is here. Don't ever forget the binaries. Now you can work it out, you can back out of it with simulations, but then it depends on your binary population. Yeah. Stellar mass functions. I'll just point out that typically the cluster mass functions on the high mass end tend to be fairly normal. They tend to be like the field. There's always a lot of argument about the low mass end, but some of the more recent results seem to suggest that the low mass end is fairly consistent with each other. I'll come back to whether it's consistent with the field if I have time. This is a really nice figure from our organizer and also another group. But basically this is showing a whole set of cluster mass functions. And of course you can see the evolution to lower masses as you increase with age. This is an age distribution. But I think there's certainly plausibility that they look very similar between the clusters. And that's kind of where the field is moving right now, but that's a bigger discussion. And I just want to point out, but it's not terribly relevant for this one, so I'll only say it quickly, but this is a 7 gig-a-year cluster, right? You'll notice all the stars are missing. You were asking about evolution of the massive clusters. Notice that the low end is missing. I'll explain why tomorrow. But this is typical IMFs. This is the cluster IMF, right? And you can just see they're missing, right? Because of evaporation, dynamical processes. And this, in the same spirit, this is showing the evolution of the typical mass in the IMF, if you want, with dynamical time. And essentially what you're seeing here is as you get to more dynamically evolved systems, the typical mass increases. Again, just showing that the low end tends to evaporate from the cluster. Okay? I can't see it, but beautiful, beautiful. All right. Homage to Blau, who I had the pleasure of meeting in the late 80s and was a truly wonderful man. OB associations, let me just briefly bring them into the discussion. The age is still greater, but not much greater, than the time scale for the loss of the natal gas. And in almost all associations, there are still parts of them that are still forming stars. Typically, the age is less than 25 megayears or so. And the reason for that is straightforward. If their internal motions are about 4 kilometers per second, which is actually kind of fast, times 25 megayears, it's 100 parsecs. So if they're unbound, and Ambartsumian argued and definitively from their densities that they are, then they can't be much older than this simply because of their dissolution time. They're associated with molecular clouds, located in the Milky Way disk, actually not much less of a scale height than the open clusters. And their masses tend to be similar to the open clusters, perhaps a bit more on the high end. The main difference between an association and a cluster is that they're unbound, which essentially is a density issue. This is a map that Adrienne made of the open clusters in the solar neighborhood. That's post-Hipparcos. I think it's actually a real honor to Professor Blau that it didn't change much. What did change, of course, is a much clearer assertion of the systemic motions of the associations. That improved tremendously with Hipparcos. But the actual local landscape didn't change that much. This is the Upper SCO association, post-Hipparcos. Really, the main goal here is just to make the point that Upper SCO is much more concentrated than Lower Centaurus, which is more concentrated than Upper Centaurus. And the idea is what you're looking at here is the dissolution of unbound systems. So in that spirit, this is the youngest, this is the oldest. You're actually seeing the systems evolve, unbind. Now, this is important with respect to Gaia. These arrows are fantastic for developing proper motion membership. They're actually not adequate yet to do internal motions. And so the internal motions of the associations are still TBD, are still to be done. About 2 kilometers per second, roughly 50 parsecs in size. Okay. This is really important for our discussions. We call them OB associations because, as Neil said, we can't see the young stars. I'm sorry, the low mass stars. But they're there. Fred Walter's done some nice work in the Orion region. This is in the belt region. This, of course, is all field, but there's the pre-main sequence stars. Preibisch and Zinniger and their colleagues did the same for Upper SCO. Again, this is SCO-Sen in its classic sense, but here's the rest of the population. Okay? And I think this really says it all. There's certainly no deficit of low mass stars in the Upper SCO OB association. Remember, Hipparcos only got down to maybe A stars. So all of this deep ground-based work to get down here and to show that, in fact, the association has the entire IMF down to around a tenth. It's hard work, but it's critical. It's absolutely critical from the formation point of view. And so again, the same slide, but now I've put associations on it as well. And again, you see a certain uniformity in the IMFs from globular clusters through young open clusters through associations. And I don't know if we're going to talk much about disks. I guess that's up to you, Kathy, at some level. But we at least need to acknowledge that the stars we're going to be talking about do have disks. And this is just a plot of disk fraction as a function of age. Okay? And you'll notice that the disk fraction drops off systematically on a time scale of about 5 megayear. That's a number worth keeping in your mind because I'm sure Kathy's going to be talking about interactions between stars. If you do n-body simulations, you're used to thinking of them as points. But now put disks around them and have them interact, it's a whole different physics. And so this time scale of about 5 megayears, this time scale of losing those disks, is going to be key for all that Kathy's about to say. Okay. Okay, I'm going to make one more very quick point, but any questions so far?
Yes,
Please.
about the OB association, since you think they are unbound, so does it suggest that they contribute more to the field than the open clusters?
The whole issue of OB associations and clusters is somewhat of an historical one, and this is going to be an important point for this meeting. Clusters are bound necessarily. OB associations are unbound. In 1930, that was a big deal. But now, if you take a broader view of star formation in molecular clouds, and you see it as occurring throughout the molecular clouds, probably more focused in certain areas, probably more intense in some areas, then what you're really looking at is certain locations that end up being bound in clusters, and the rest of it which will necessarily dissolve as the gas disappears. Associations are nothing more than the sort of inevitable consequence of star formation going on throughout a cloud without global densities high enough to remain bound. So the question you're really asking, that was a long-winded answer to say, we need to understand what fraction of stars are formed in small-scale, high star formation efficiency regions in clouds compared to the whole cloud. And whether they're OB associations or T associations or clusters is kind of a historical jargon, is what I'm getting at. So, to answer your question, are most stars formed in OB associations? I think the real question is, are most stars formed in unbound groupings? Are they OB associations? That depends on whether or not there are OB stars there. So, all right, let me just make one last comment just for fun in case you want to ask me at lunch. And this gets back to Neil's point again. 2 slides, that's all I'm going to show, maybe just this slide. Any of you who have ever taught have seen this picture. This is what we teach our students. This is the evolution of color magnitude diagrams. And one of the classic clusters on this picture is M67. This was the second cluster that Sandage and Schwarzschild did in the 50s. First one was M3. It's classic, it shows evolution, and there it is. There it is too, all right? Except that's a lie, okay? Because what really, the members of that cluster really look like is that, okay? These are all 3-dimensional kinematic members. That's what we tell our students. That's what you think in your mind, I bet you. And that's reality. And these are easy to explain. They're just the binaries. But the sub-subgiants, the blue stragglers, the yellow subgiants, they constitute roughly 10% of the population in this part of the cluster that we always talk about. 10% of the evolution. 10% of the stars have non-standard evolution from what we teach in our classes. And I was going to explain it all to you, but I don't have time. But I just want you to know, as an aside, my parting comment as a stellar evolutionist is that there is a whole set of stellar evolution paths, non-standard, non-equilibrium stellar evolution paths that represent the interface of 2 great fields of astrophysics, stellar evolution, stellar dynamics. And if you decide that star-forming regions in Gaia aren't where it's at, come talk to me about colliding stars. It's a lot of fun. All right, enough for the first lecture. Have lunch.